So let's go to example 8. In example 8, we have a rigid tank which contains a water vapor at 250 degrees C, but we do not know the pressure. We do not know the pressure. When the tank is cooled to 124 degrees C, the vapor will start condensing, and we need to estimate the initial pressure in the tank. Okay? Again, spend some time to do this problem. Okay, so I assume that you have done this problem for many days. So let's see the solution. Well, here we have a rigid tank. Rigid tank just means having a constant volume. Okay. In the previous examples, you will see that I have used this word rigid tank for so many problems, but you will see how this word rigid play a role here. Okay. So here we see that because it has a constant volume and this tank has contained all of the water, so the specific volume remains unchanged. In this case, if we would like to estimate initial pressure, first we look at because the volume is constant due to the word rigid, and no mass would either gain or loss inside this rigid tank because it's a closed system. So let's find the probability first. At a 124 degrees C, we know that the specific volume at state 1 as well as state 2. Okay? State 1 means the water vapor at 250 degrees C, while state 2 means at 124 degrees C. Will be equal to, because at 124 degrees C, the vapor will start condensing. It means that at 124 degrees C, the vapor is in a saturated vapor state. So it's equal to Vg at 124 degrees C. Okay. What table should you consult? Because we have a temperature, so we go to table A4. Again, unfortunately, you will see that we just have the temperature of 120 and 125. Okay, so how can we get the term for 124 degrees C? Then we need to use the method called the linear interpolation again. But in this case, we know that it's an increasing function. Okay, from 120 to 125. You can divide it to 5 portions, and because we need 124 degrees C, so we just get 4 portions of it. Okay, what do I mean is that because at 120 degrees C, the specific volume is of this value. And then if we would like to get the term at 124 degrees C, because we have a term for 125 degrees C, we just need 4 over 5 of the difference between 125 and 120. What do I mean is that this one is the value for 125 degrees C, and this one is the value for 120 degrees C. Okay, the difference indicates the increment of specific volume between this range 120 to 125. Okay, of course it's a linear increment. If we would like to get the value at a 124 degrees C, we just divide it by 5 to get the increments for 1 degree C and multiply by 4. So we can guess the increments for 4 degrees C. So if you add it to the original value, then you can get this one, the value of the saturated vapor at a 124 degrees C. Okay, of course you can use the original method, that is you draw a line and then use the slope equal to slope method to find out this, but you will get the same result. Okay. So after that, because when the tank is cooled 124 degrees C, it starts condensing. That means at a 250 degrees C, because we have the same specific volume, and this temperature is greater than this, in this case, it means that the vapor is superheated. At 250 degrees C, it's in a superheated state. As a result, we would have a pair of value to find. T1 equal to 250 degrees C. And the specific volume will be 0.79436 meter cube per kg. Okay. As a result, we can guess the pressure. Okay. We will go to the superheated water table. That is table A6. So at 250, in this case, the volume is of this value is small. So you go further and find at a pressure of 0.3 megapascal, you will see that at 250, you have this value, 0.79645. What's the original value that we have found? Okay, it's 0.79436. Okay, so here, because we have only the tables for separate pressure, and we know that this value 0.79645 is very close to our desired value. So for simplicity, we just find out this pressure. So this pressure is equal to 0.30 megapascal. This one is just for simplicity. Okay, of course you can get a more accurate value. So this is from table A6. Okay, so because we have separate tables for different pressures, so you need to see at this temperature whether the specific volume is equal to this value or very, very close to this value at certain pressure. In this case, we find that at a 0.3 megapascal, the specific volume is very close to this value. So for simplicity, we just take this value, and this completes our problem. Okay. So let me go through this problem again. So because we know that when the tank cools to 124 degrees C, it starts condensing. And we know that because of the fixed mass and the rigidness of the tank, the specific volume is constant. So we can conclude that in a 250 degrees C is in the superheated state. Okay? But how can we find out the properties for the superheated state? Because we just have this temperature, and we need one more property to fix the state. In this case, because we can find out the specific volume, so we also use the specific volume to fix the state. As a result, we will first find out the volume, and we know that the volume at stage 1 and stage 2 are the same, which is equal to the Vg at 124 degrees C. Okay, and because at 124 degrees C we do not have exact data in the property table, so we need to use linear interpolation. Okay, and because we can find out the value at 120 and 125 degrees C, so we can go to the table and find these two values, and noting that at 125 is this one, and at 120 is this one. Okay, and we can think of it as the difference of the specific volume over this 5 degrees C, and because of linear interpolation, so it would decrease at a constant rate. Okay, so we would divide it by 5 to get a decrease for 1 degree C, and we just multiply by 4. Okay, so that when we add this value 120 to this term, we can get the Vg at 124 degrees C. Okay, so if you still don't know what I mean, is that I have this graph, okay, and I have this line, and I have the point here and here, and if I would like to find out the value at 124, then what should I do? Because I have the difference from here to here, and noting that because it's a straight line, so it would decrease at a constant rate. So in order to find out the term at 124, we start 120, and we get this difference divided by 5, and then we get 4 portions of that. Okay, we get 80% of this difference, so we can get the term at 124. Okay, and we have got the specific volume, and with this temperature and this specific volume, we can fix the state because we have two independent and intensive parameters. And you check the table, and you will find that for simplicity, it will be this value from table A6. Okay, so we have finished example 8.